Let me content for a second camera. Share. Okay, so welcome back everyone to our lectures. So this is an outline of the next topics of the Tuesday lectures. We're going to have state transfer in trees today. Next Tuesday, we're going to have a lecture by Yasser Omar, and I can only guess he's going to speak about search. Then my final lecture will be about instantaneous uniform mixing, which will actually also be an advertising for a workshop in May. Chris will be advertising to all of you soon, I suppose. And then Chris is going to deliver the final lecture on average mixing matrix in 4 weeks. So recall that if we have perfect state transfer, so this is the equation as you all are very used to by now, for some real number t, complex number lambda, then for all eigenvalues whose projection of the characteristic vector of the vertex onto the eigenspace is non-zero. And now, well, I'll keep repeating this just simply because I think it's easier for everyone to keep track of what's going on. But the eigenvalues that would satisfy this condition are, we say that they belong to the eigenvalue support of the vertex A. Okay, so these are the eigenvalues for which A and the projector satisfy this condition are the eigenvalues within the eigenvalue support of vertex A. So we know that if perfect state transfer occurs, as we have already discussed, then for all eigenvalues which belong to the eigenvalue support, it must be that the eigenvalue is a quadratic integer of this form. Okay, so not only the eigenvalue can be written as A, well, plus some BR square root of delta over 2, but also this thing must be a quadratic integer, which means this is either an integer, in which case simply assume that A is 0, delta is 1, and BR is even. Okay, or this is a multiple of delta, in which case assume A is 0, BR, the BRs are even, or you have now two options, either A is not 0 and both are even, in which case again, the over 2 here cancels and you have an integer plus an integer times square root of delta. Or A is not 0, both are odd, and in this case, delta must be congruent to 1 mod 4. So if delta is congruent to 2 or 3 mod 4, then we know that we must be in this case 3, cannot be case 4. So this is a classification of quadratic integers, very old due to Dedekind. And of course, this is elementary. If you simply solve a degree 2 equation and you look at the formula to solve degree 2 equations, you can very easily arrive at this classification. Now, so for all eigenvalues in the support, they must be of this form. And then what I want to start today is this information that if we have UV perfect state transfer, I swapped AB to UV because now there is another A. I realized that I'm overusing A. So A here is a vertex, A here is a number. Now, in this theorem, A would be a number, so vertices would be U and V. Then you have UV perfect state transfer in a bipartite graph. Because of this classification of quadratic integers, we can show that A must be 0. And why is that? Well, it's a very simple thing in algebraic graph theory that if some theta is an eigenvalue of a bipartite graph, then so is minus theta. And the reason is very simple. You can write the adjacency matrix of a bipartite graph as such. So you have 0 representing that there are no edges in the first class, 0 representing no edges in the second class, and you have the matrix which gives you the adjacency between the two classes, right? B and B transpose. So this needs not be a square matrix, of course, depends on the number of verses on each class. And then you multiply this by an eigenvector, and I'm splitting the eigenvector into two parts. The part x indexed by the rows, by the columns here, and the part y indexed by the columns here. So this is an eigenvector. I'm assuming this is an eigenvector to the eigenvalue theta. And then it's very easy to notice that if you simply sign one of the entries, you still have an eigenvector, but now for the eigenvalue minus theta. It's simply a matter of performing this matrix multiplication here. So the result here is going to be a vector which is by on top, b transpose x on the bottom. And exactly if instead of y have minus y, then you get this signing on the eigenvalue. So for all bipartite graphs, if something's an eigenvalue minus something is also an eigenvalue. And then if you have an eigenvalue which is written in this form, it is, and as you can see, because the only difference on the eigenvector is assigning, I'm not changing the eigenvalue support. So if this eigenvector is non-zero in a particular entry, then this eigenvector is also non-zero in that particular entry. So the eigenvalue support, so meaning if this eigenvalue belongs to the eigenvalue support of a vertex, then minus itself also belongs to the eigenvalue support of the same vertex. Now, we have that theta is written in this way, minus theta is going to be written in this way. And then if there is perfect state transfer, it must be, so the A here is the same, is fixed. A and delta are the same. They do not, if you vary the eigenvalue, you're allowed to vary the B's, but not A and delta. A and delta are determined. If there is PST, it must be for one only A, one only delta, which works for all eigenvalues in this one. All right, we saw that. So it must be that A is equal to minus A, and this is not true unless A is equal to 0. So if the graph is bipartite, we can see that A must be 0. So there are exactly only two options, which is either the eigenvalues are integers or they are multiples of square root of delta for some delta. It cannot be an integer plus a multiple of square root of delta. Okay. Any questions? I have no idea why I stapled this. Hold on a second. Okay, now, so there is this result due to Chris from the 80s, a paper, very nice paper called Invertible Trees, I think, which says that, well, if G is bipartite and has a unique perfect matching, then the adjacency matrix is invertible and its inverse is an integral matrix. Okay, so the condition here being very special, the condition that G has a unique perfect matching. Okay, now if the graph is a tree, then, well, every perfect matching is also unique. And you can even show the converse. You can show that A is invertible if and only if the tree has a perfect matching. In which case, of course, because trees are bipartite, if the tree has a perfect matching, okay, then the inverse of the adjacency matrix is integral. Means the determinant is plus or minus 1. Now, with that information, we can show that except for the path on two vertices, no tree which has a perfect matching also has perfect state transfer. And it has to do with this eigenvalues. I mean, we have just seen that if a bipartite graph has perfect state transfer, then the eigenvalues in the support of the vertex involved in perfect state transfer are either integers or quadratic integers. But now we have the extra information that the inverse of the adjacency matrix is an integral matrix. Therefore, its eigenvalues are also algebraic integers. They cannot be rational. So if there is perfect state transfer, theta is in the support of the vertex involved. So theta is a quadratic integer. It is written in this form with a equals 0. But also 1 over theta is a quadratic integer because it is it is an algebraic integer. That's what I meant to write here, but nevertheless, it's an algebraic integer. And the interesting thing is, if something is an integer or an integral multiple of square root of delta, 1 over this thing is an algebraic integer if and only if this thing is plus or minus 1. right? So if that is 2, for example, then a half is not an algebraic integer. It is an algebraic number, but not an algebraic integer. And if this is, I don't know, 3 times square root of 5, then 1 over 3 times square root of 5 is also not an algebraic integer. The only options are plus and minus 1. And this is basically saying that the only eigenvalues in the support of the verses involved in PST are plus and minus 1, and then it's not difficult to see that this means they live, these verses are in a connected component which is isomorphic to P2. There's also a nice side exercise implicit in this proof. So, and because a tree is connected, the tree itself must be P2. So this is exactly the only tree which has a perfect matching and which also admits perfect state transfer. We already know P2 admits perfect state transfer, right? So no other tree with a perfect matching does. We do have some other results about restricting perfect state transferring trees, but nothing much stronger. I mean, or at least nothing that looks as nice as this one. Well, you can check. I think all results basically. I have this paper from 2015, which has a bunch of them. I think since then, very few things we have advanced on this. So if you actually want to know, maybe on the book we have more results, but if you want to know the current state of the art in this question, you can ask us later. But now I'm willing to make this conjecture. I've been willing to make this conjecture now for some time that other than P2 and P3, no other tree admits PST on the adjacency matrix model. Okay, and this is basically because it's very easy to find results which indicate first that perfect state transfer does not like graphs with few edges compared to the number of verses or the diameter, and more than that, it's very easy to find results restricting or limiting PST on trees. Now, this question seems to be perhaps a bit too difficult at this point. So, I mean, we can settle for intermediate things. For example, this says that if there is a perfect matching, no PST, it would be very nice, for example, to have a result saying, well, what if there is a maximum matching that exposes only one vertex, for example? I mean, does it still imply something? That would be quite nice, actually. Okay. So this is a conjecture, and I would say it's perhaps one of my favorite problems, one of the problems I'd like to see solved. This actually has received a failed attempt on arXiv a couple of years ago. Some people thought they had proved this result, but there was a flaw in their proof, which actually made me not sure. Well, I can't say that I was happy for them, but I was happy because of having made a conjecture that received a failed attempt. Anyway. But what I want to focus now is what if we change the model? What if instead of the adjacency matrix, we use the Laplacian matrix instead? Okay. Now, the interesting thing is with the Laplacian matrix instead of the adjacency, not only we can say the eigenvalues are quadratic integers, we can be even more specific and show that the eigenvalues must be integers. And the reason is very simple. The reason is because 0 is always an eigenvalue of the Laplacian matrix, which belongs to the eigenvalue support of all verses. 0 is an eigenvalue with the corresponding eigenvector all ones. And if the graph is connected, this is indeed the only eigenvector of the eigenvalue 0. And this implies that if all the eigenvalues in the support of the vertex are of the form a plus or minus b square root of something divided by 2, then a must be 0. Right? Because the a is the same for everyone. So a must be 0. And therefore, all the eigenvalues are of the form b times square root of delta. But then if something is an eigenvalue of a matrix with integral entries, then all of its algebraic conjugates also are. Won't really have time today to go into the details of what it is an algebraic conjugate, but I mean, this is, perhaps I've seen this before. So b square root of delta is an eigenvalue, so minus b square root of delta is also an eigenvalue. But the Laplacian matrix is positive semi-indefinite, as you've seen, I suppose, in one of the exercises early in the course. All eigenvalues must be greater or equal than 0. So no eigenvalue can be of the form b times square root of delta. All eigenvalues must be integers. So this is a consequence of this classification. This classification works for the adjacency matrix, but in fact it works for all symmetric matrix with integral entries. This classification, this result exhibiting the nature of the eigenvalues in the support of a vertex involved in PST, right? So either integers or multiples of something, or things of the form a plus or minus b squared with delta over 2 perhaps, but a must be 0. Things cannot be simply multiples of delta, so the only option remaining are the eigenvalues must be integers. Any questions now? I see here in the chat. Oh, Chris already replied. Very good.
I think you answered. You answered before he did. So I was.
Yeah.
So it seemed to me that you were saying. So it seemed to me that you were saying theta r has a conjugate, and the conjugate must be the negative of theta r, and because negative theta r is an eigenvalue. But imagine that some alpha and its conjugate are both eigenvalues, and minus alpha and its conjugate are both eigenvalues. So I think that the proof is that the a and the delta don't change. The a and the delta cannot change, right? So it's not that the conjugate of theta, algebraic conjugate of an irrational theta r must be negative theta r. It's that you're saying that the a and the delta cannot change.
Yes, the a and the delta cannot change. Yes, yes.
It seemed to me that you were assuming that minus theta was the conjugate.
No. Yeah, okay. No. It's the a and the delta. So that's the yes. That was from the previous page, I suppose, right? So I only saw that. I was trying to, yes, so it was here. Yeah, no. So it's about the a. So the a has to be the same. So the thing which is not multiplying square root of something cannot vary. So that's the tricky thing. And then that's the so a must be 0.
Thanks.
Actually, it's perhaps a good moment to remind you guys that we do have an open problem, which is to find an example of perfect state transfer using eigenvalues of the nature of the form either 3 or 4. We do not know any such example. So it is actually an open question whether such an example exists or if this can be restricted even further. We do have examples. So this result actually is not, so this result is such, if A is periodic, then the eigenvalues must be of this form. And we do have, so you only need to assume that the vertex is periodic to show that this, the eigenvalues must be of one of these 4 forms. But, and we do have examples of periodic vertices with eigenvalues which look like 3 or 4. However, we do not have examples of vertices involved in PST, which eigenvalues are of the form 3 or 4. So it's actually an open question if PST on top of periodicity can allow you to rule out these 2 options. We do have, of course, many examples of PST with eigenvalues, either integers or multiples of the square root. So yes, so the question now, state transform trees, how about the Laplacian, the model with the Laplacian matrix? We do know that the eigenvalues must be integers. Now, how can that help us? So.
Wait, sorry, can I ask you a quick question?
Of course, please.
It sounded like you were, how general was the statement that you just made? Because it sounded like that's rolling out a lot of possibilities.
Which statement, sorry?
About not having examples of eigenvalues of the second 2 types in graphs with PST.
Yes, so we have never found a graph, 2 verses admitting a state transfer between them, whose eigenvalues in the support are of the form a plus something square root of something over 2, perhaps.
Okay, so all
yes.
of our examples are
1 and 2. Yes.
Wow. Okay.
So it is indeed a question of well, it is possible that you can show this is not possible.
Okay.
Yes, we have tried, but it doesn't seem. I mean, it doesn't seem that the conditions PST imply on top of periodicity are strong enough for us to achieve this.
Okay, but this is for, you're saying this is for all graphs, not like specifically for bipartite or trees.
No, for all graphs, unweighted though.
Okay.
So for weighted graphs, I can construct examples satisfying anything here. I can choose my eigenvalues, and using the technology of orthogonal polynomials from 2 weeks ago, I can choose my eigenvalues and I can construct my weighted path with PST. So unweighted, it doesn't need to be bipartite or a tree or anything. We only have examples with 1 and 2.
Wow. Okay.
Yeah. It would be very nice result to us. I mean, I wouldn't say particularly interesting in terms of the consequence, but I would be very curious to see what technique would allow for PST to imply this no-go for 3 and 4.
Interesting. Yeah, okay,
Yeah.
Thank you.
Sure. If you're interested later in this question, I can share with you a couple, well, the failed attempts so that you don't repeat them.
Okay. Yeah, that would be great.
Yeah. So what's the result now? So we have a graph G versus A and B, Laplacian matrix. I'm already telling you what is the spectral decomposition. In general, I will be assuming that lambda 0 is actually equal to 0. I know 0 is always an eigenvalue. Oh, where's my pencil? It's right here. I will be making the assumption that lambda 0 is actually equal to 0. I know 0 is an eigenvalue, so I'm simply saying that the index of the use the same index as the value. Anyway, so PST implies it's actually if and only if. Well, this is to say the verses are strongly co-spectral. Because 0 is always an eigenvalue with eigenprojector 1 over n times j, it's not difficult to see that gamma, the phase here, must be equal to 1. And if an eigenvalue belongs to the eigenvalue support, this eigenvalue must be an integer. Okay, this is skip this, but to remind you, the Laplacian matrix is the Laplacian. This is a matrix that has the degrees of the vertices in the diagonal entries and minus the adjacency matrix on the off diagonal entries. Okay, so it's degrees on the diagonal. So it's different than the adjacency matrix because, well, it has perhaps non-constant values in the diagonal. Okay, if the graph is regular, then it really makes no difference to use either Laplacian or the adjacency matrix model because you're simply multiplying the matrix by -1 and adding a multiple of the identity, and that doesn't change much what happens here, the exponential of ITL. But if the graph is not regular, then these degrees are not constant, and this actually creates a completely different model. All right. Now, this is what we have. And then, of course, the parity condition that determines the state transfer is actually more simply stated here. If you recall from our lecture, I don't know, a month, 2 months ago, we had that thing with the differences of the eigenvalues, but now, fortunately, 0 is always an eigenvalue. So instead of looking at the differences of all the eigenvalues with a fixed eigenvalue, we can simply look at their differences with 0, meaning themselves. So if G is the GCD of the eigenvalues for which the projection is non-zero, meaning the eigenvalues and the eigenvalue support, then we have equality in the projection if and only if the eigenvalue divided by this GCD is even. And we have minus if and only if this ratio is odd. So this is immediate consequence of the state transfer characterization we saw. Okay. And for whatever follows into this lecture, I'm introducing yet new notation. Whenever this is the case, I will say that lambda r belongs to the positive eigenvalue support of the pair of verses A and B. And whenever this is the case, I will say that lambda r belongs to the negative eigenvalue support of the pair of verses A and B. Okay, so this is simply my new notation. And I think this is perhaps, no, this is not the last new notation I introduced today. I know that these 1 hour lectures, lots of things are a bit tough to follow, but please, if you forget at some point what this means, ask me again. All right, but this is simply to identify the eigenvalues for which the projections are equal, the eigenvalues for which the projections are minus each other. All right, so these are the three conditions that, if satisfied, imply PST, and PST implies that these conditions are satisfied. And now I'm gonna make heavy use of this third condition to restrict the possibilities of state transfer and trace, according to the Laplacian matrix, of course. So the first thing is, well, if there's only one eigenvalue for which the projections are minus each other, you can show that the vertices are twins. And that's actually true for all graphs, not only trees. For all, according to the Laplacian matrix. Here's the proof. The proof is actually quite simple. I will be defining these two vectors, ket z plus and ket z minus. I keep forgetting to use ket. As you can see, I first wrote z plus and then I squeezed in a ket here, but I'm trying to get used to it. I think it's actually I'm getting more and more fond of this notation. Anyway, so ket z plus will be the sum of the projections according to the eigenvalues in the positive mixed support. So there's an A, B missing here. And the ket z minus will be the sum of the projections with the, according to the eigenvalues in the negative support. Right. Now note that if I sum ket z plus and ket z minus, I'm summing the projections of A here, summing the projections of A here, and these are all the eigenvalues in the support of A. So in fact, the sum of the, I'm simply summing the projections, and the sum of these projections is indeed A. I recover A, ket A. So ket z plus and ket z minus is actually equal to ket A, and these guys are equal to FRB, and these guys here are equal to F minus FR ket B. So in fact, if I make ket z plus minus ket z minus, this minus cancels with this, and I recover ket B. Okay? Now, if there is only one eigenvalue in the negative support, it means that this sum has only one term, and this is in fact an eigenvector. This will be the projection of ket A onto the eigenspace of the only eigenvalue in here. And this eigenvector, because of these equalities, two red equalities that I showed, is actually 1/2 ket A minus ket B. So if there is only one eigenvalue, this is an eigenvector. Of course, if there is PST, right? Sorry, if A and B are strongly co-spectral. If A and B are strongly I'm assuming, okay, A and B strongly co-spectral. Yeah, this is strongly co-spectral. But this is sort of implicit in the definition of this symbol. So, but let me just leave it clear here. Okay, now, ket z minus L times ket z minus equals lambda ket z minus implies that, so now this is the eigenvalue equation which I can examine row by row, and this means that for all vertices of the graph, if you simply look at a row versus different than A and B, this equation is the same thing as saying that the degree of W, which appears in L, minus the sum over the neighbors of W of the corresponding entries in ket z minus is equal to, so this 0 here is the W entry. So this 0 is the W entry of ket z minus. And I know that this is 0 because ket z minus has only is ket A minus ket B. And I'm looking at verses which are different than A and B. So the degree of W times its corresponding entry in ket z minus corresponding entries over the neighbors of W is actually equal to 0. 0 again, because this 0 here is lambda times the corresponding entry of W in Z minus. And this is 0. So if A is a neighbor of W, it must be that B is a neighbor of W and vice versa. I have 0 here, 0 here, and therefore, if one of these entries is non-zero, there must be another one. And the only possibilities are either A or B. Okay. So this shows that if there is only one eigenvalue in this negative support, it must be that the two verses are twins. Everything which is a neighbor of one of them is a neighbor of the other. They could be twins, or in the graph theory community, people refer to these things as, well, they could be twins or false twins, whether or not they are neighbors to each other, and that is allowed here. But I'm overlooking this detail. I'm simply saying that everything which is a neighbor of one of them is a neighbor of the other. The two of them could or could not be a neighbor. The two of them could or could not be neighbors. Okay. But of course, if the graph is a tree, they cannot be neighbors and share a common neighbor. Otherwise, there will be a cycle. Now, continuing. Let's now start with T, a tree. It's Laplacian matrix as we've been examining. This is the eigenvalue equation. L times ket z is lambda times ket z. Then for all verses, this is the, I'm actually making that equation from the previous page more explicit now. So this is what you recover if you examine the eigenvalue equation row by row. Okay. Now, say lambda is an integer. Ket z is an integral vector. So of course, L is an integer. If lambda is an integer, you can use row reduction to find an eigenvector which is integral. Okay, you simply do your row reduction, you're going to find something which is rational, and you scale up in general. All right. So you have an eigenvector which is integral, and simply assume it's being scaled so that the GCD of the entries is actually equal to 1. Always possible. Now, assume W is a leaf of your tree, and thus its degree is equal to 1, and say V is the unique neighbor of W. Now let's look at this equation up here again. We have that the degree of W, which is 1, times its entry on Z, minus the sum of the entries on Z of its neighbors, but there is only one neighbor, is actually equal to lambda times something, so it's congruent to 0 modulo lambda. Lambda is an integer, so I can look at this equation. This equation has only integral elements, so I can look at this equation Z lambda. It means now that all entries of Z are congruent to the same thing modulo lambda. Because you can simply keep pruning trees and repeating this argument. Sorry, keep pruning leaves and repeating this argument. So you find a leaf, you find this thing, you find another leaf, you keep going, keep going, keep going, and eventually you can show that all entries of ket z are congruent to the same thing modulo lambda. In particular, they cannot be all congruent to 0 modulo lambda because the GCD of the entries is equal to 1. So they're all congruent to something non-zero modulo lambda. Okay? For all eigenvalues. Now, if there is AB, PST, A and B are strongly co-spectrum, if lambda r is an eigenvalue which belongs to the negative support, it means that for all eigenvectors corresponding to lambda r, which I am denoting by ket lambda r, this is a standard, this is Dirac's notation on its prime. If lambda r is an eigenvalue, denote a corresponding eigenvector by ket lambda r. If this is true, if the projections are minus each other, it means that for all eigenvectors corresponding to lambda r, the entries corresponding to verses A and B are minus each other. All right? But see, all these entries are also congruent to the same thing modulo lambda. Okay. And with that, strikes me now I could be saying that it is lambda r is 1, 2, or a power of 2, I suppose. Or even, right? What's happening here? What am I missing? Lambda is 1 or 2, that's for sure, but it also could be an even number. No. Do I want to say that lambda must be a prime or 1?
Does it have anything to do with you making the entries in the eigenvectors?
Sorry?
Does it have anything to do with you making the GCDs of the entries of the eigenvector being 1?
Yes, right? Because they could, yes, I think you're right. I think you're right. Yes, because if they're all, let's say, congruent to, if they're all congruent to 8 modulo 16, their GCD is not 1. Very good. And if they're all congruent to 15 modulo 30, they're also, yes, I think you're right. I think you're right. Yes, thanks, Ada. Yes, so I believe you. It's an exercise for all of you guys to also believe Ada. That's very good. Thanks. Now, so these are the only options, thankfully. But it can't be that 1 over G and 2 over G are both odd. G, of course, the GCD of these things would have to be either 1 or 2. It can't be that these things are both odd, so there can only be one of them actually in the negative eigenvalue support. And so A and B are twins. So this has just shown all of us that if there is perfect state transfer on a tree according to the Laplacian matrix, the two verses must be twins. The only integer eigenvalues which can belong to the negative support are 1 or 2, but not both of them can be there because G is, these two things cannot be both odd, and they have to be odd for the negative things according to the classification of PST. So I'm making a heavy use of the classification, the characterization of PST. Right? So the size of the negative eigenvalue support is 1. The two vertices are twins. So this is showing that if there is perfect state transfer on the tree according to Laplacian matrix, it must be between two verses that look like this. Well, or they are neighbors, or this is the case, right? The path on two verses is also allowed. Of course, if the two things are neighbors, they cannot have a common neighbor, otherwise the graph is no longer a tree. And also here, they cannot have two common neighbors, otherwise, again, the graph is no longer a tree. So it's either this case or this case. Now, I can even show that if this is the case indeed, lambda is not equal to 2, it's actually equal to 1. And this is again a consequence of the eigenvalue equation examined row by row, in which case I'm examining the row regarding vertex A. So the degree of A, so look here, is always the degree times the entry minus the entries of the neighbors is equal to lambda times the entry. So degree of A times the 8th entry minus the sum over the neighbors of A is equal to lambda times the entry of A. Now, I do know that if the size of this thing is equal to 1, the corresponding eigenvector is ket A minus ket B. And that's what I'm using here. And I can simply conclude that lambda must be equal to 1. Because this is 1, this is 0. So I have this equals this, lambda must be equal to 1. So very restricting Indeed. But now the final argument is that we can explicitly rule this case out. So this is a situation. We have a tree. Let me put a T here. This is a tree. We have two verses which are twins, A and B. KZ plus, which is the sum over the projections of A, FR. KZ minus, which is the sum of the projections of A on negative support, positive negative support. As we have seen, this is equal to 1/2 ket A plus ket B. This is 1/2 ket A minus ket B. Very good. Okay. Now, what can we say now? First observation. So L times the projection of A onto FR is lambda R times the projection. And now I'm simply going to multiply this equation from the left, taking the product with ket A. I'm going to examine the 8th row of this vector equation, which tells me this. And now on the left, I have ket A, FR, ket A, minus, so this is coming from the fact that A is a leaf, right? So the diagonal entry on L corresponding to A is equal to 1, and then I will be summing over the off-diagonal entries corresponding to the neighbors, but there is only one guy, which is ket W. So this is again really making this eigenvalue equation explicit on each row. And then the conclusion is that ket W FR ket A is equal to 1 minus lambda R, bra A FR ket A. Bra W FR ket A. Now, another thing is, because Z is a sum of ket A and ket B, the Wth entry of Z plus is 0. But ket Z plus is the sum over these projections. So I have this equality here. And now I'm using this equality to replace ket bra W FR ket A by 1 minus lambda R bra A FR ket A. So I have that 0 is equal to this. Now, 0 is always in the positive eigenvalue support. So 0 is always one of these guys. And its corresponding entry is always 1 over n, because its corresponding eigenprojector is always 1 over n times j. Right? 1 belongs to the negative eigenvalue support, as we've seen in the previous page. So if anything else belongs to the positive eigenvalue support, this thing must be greater or equal than 2. So here I have a sum of where one of these elements here is 1 minus 0, and all other elements are negative numbers smaller than minus 1. These things, on the other hand, are always positive, because these are the diagonal entries of positive semi-definite matrices, projection matrices. So this is going to be 1 times something positive plus a bunch of negative things smaller than minus 1 times positive things. So this whole expression is less or equal than 2 over n minus this whole thing here. And this is simply, well, 2 over n. Why? Because 2 over n minus the entry, the term of the sum corresponding to the eigenvalue 0 is 1 over n. And this is indeed already here. And all the other negative things are more negative than minus 1. They're smaller than minus 1. So I'm replacing, I'm increasing these things, right? But this is what we get. So this whole sum here is less or equal than 2 over n minus this. But I know what this is. This is the 8th entry of ket Z plus. And cat z plus is a half. And this is a half times cat A plus cat B. So the 8th entry is a half. So this is the inequality. 0 less or equal 2 over n minus a half. So n is at most 4. And then n is the number of vertices in the graph. And you're left with very few trees to check if there is PST, and none of them does. So the only tree with PST is P2. Okay, according to the Laplacian matrix model. It's actually, I'll leave it here as an exercise to you guys to generalize this argument of the twins and show that if a graph, not necessarily a tree, is neither of these three options, because all these three options admit PST, they all have at most 4 verses, and these three options admit PST according to the Laplacian matrix. If you have twins, neighbors or not, sharing 1 or 2 common neighbors, you can still show that there is no 8B PST. So there's a more general thing. So for graphs in general, twins do not typically have PST if they have few common neighbors. Okay, and the argument is basically repeating this, but without making the underlying assumption that the lambda 1 is in lambda minus, or that the A and B are twins in a unique tree. So you can, this argument still applies with some room, and this room is for you to assume, to admit the verses to be neighbors or not, which we are not, and also that they could share 2 common neighbors still, and you're still good to go. Okay, so this is it. I have some more comments to make. As a result, no PST on trees is due to myself and Henry Liu, back from 2015, I think. Our original proof was more complicated than this, and for some time, actually, it completely eluded me that it could be as simple as this one. What was more complicated? Hold on, let me find it here. This thing with the ruling out twins is still necessary. However, this argument to show that the eigenvalues are either 1 or 2, either equal to 1 or 2, by simply examining the eigenvalue equation row by row, as we showed you guys here. Our original argument used what is known as the matrix tree theorem, which says that the n-1 by n-1 determinants of the Laplacian matrix count spanning trees. And of course, if the graph is a tree, there is only one spanning tree, which is the tree itself. So the rank of the Laplacian matrix over ZP is always equal to n-1 if the graph is a tree, or, well, if P is odd, or has a number of spanning trees which is a power of 2. So this basically tells you that this basically allows you to know which are the eigenvectors of integral eigenvalues, right? You do know, if you assume that there is a pair of verses which are strongly co-spectral. So you can, because the determinant of n-1 by n-1 submatrix is 1, that matrix has still linearly independent columns over ZP, and therefore you are able to describe which is the only eigenvector that could be in the kernel, right? Which is the all-ones vector. And so this is a more sort of like more general thing. It's slightly more complicated than what I showed you, but it allows you to derive a stronger or a more complete information, more general information. So the the most general theorem I can say is this. If you have a graph on inverses with at least five vertices, if the number of spanning trees is a power of 2, and if there is a BPST according to the Laplacian matrix, then it must be that they are twins. If they are neighbors, they must have at least 3 common neighbors, and k plus 2 must be a power of 2. And if they are not neighbors, they must have at least 3 common neighbors, and k must be a power of 2. And well, I've given enough information to this lecture for you to at least try proving this theorem. It uses this fact, so you will have to think a little bit. This is certainly challenging to simply reading these understand exactly what's going on, but it is a nice challenging exercise. And you add to this small exercise that I put here, and you will be able to, you will have enough tools to try to show this result. If you simply want to see this proof, you can check the paper by myself and Leo. It's on sigma, and I think the title of the paper is No Laplacian Perfect State Transform Trees or something. It's from 2015. Okay, all the results are there in the paper. You will see that indeed we took this path to show, which is more general. Back then we thought this was the only way. Of course, by now we have this much simpler thing, which I actually learned from Harmony, which has been giving you guys lectures on Thursday. As far as I know, Harmony, Ada, and some URAs showed results about FR on trees using this much simpler argument to deal with these congruences of the entries of eigenvectors, right? But the more general thing allows you for a more general result, which if you guys want to be brave, you can try to prove. Okay, that's it. Thanks, everyone.
Thanks, Gabriel. Questions?
Can I ask Gabriel to just summarize? As far as I understand, you've proven today that for the Laplacian matrix, P2 is the only tree, and for the adjacency matrix, as long as there's a perfect matching, then P2 is the only tree, but the other part is largely open. Is that what's left?
Yeah. Trees for the adjacency matrix model, which do not have perfect matchings. We only know P3 as an example having PST, and we know that no other path that meets PST, and we can show several more restricting, there's a bunch of things are also here on this paper, several more restricting arguments. So we can show that if the verses are in different color classes, then 0 must be an eigenvalue. Or, I mean, we can show several, we can restrict very many cases, but not really display another big class, which do not admit. As far as I know, it's even open whether or not twins on adjacency matrix could have PST. This, unfortunately, this same argument that I showed here really depends on us using the Laplacian matrix. You cannot really adapt it immediately to show that twins do not have PST on trees according to the adjacency matrix. There's what is it? This one here is quite important. It's coming from the degree in the entry in the diagonal entry. So it's,
Thanks.
No questions? Okay, I'll shut the recording down.